Hey, we've been hard at work here at AMSOIL. We've built an LS-based engine. It's making 1,000 horsepower. We've put it in some cool situations on our dyno, such as drag racing, autocross, and even some daily driving. Well, we've taken it apart and we're here to show you the results. So let's get into it. We built a motor, we ran it on a dyno, and now we tore it all apart. Garrett, how did we get here?
Len, we landed on the LS because it's a very robust system. It's very popular and the aftermarket for it is very deep, which allows us to build this engine how we wanted to build it.
Tell them what the goals were for this engine.
Yep, the goals were 1,000 horsepower. We want to run on pump gas. We want it to be able to be driven on the track and also be a daily driver as well. So we ended up running it in 3 different areas, 3 different test parameters. We did a drag racing simulator, we did autocross, and then at the very end, daily driving.
We took all of those different things and we stuck it all together, which is what kind of made it extreme, right? We did the drag race and the autocross thing, plus we daily drove it. The average person may just do one of those.
Exactly.
How did we come up with that drag racing profile?
The dyno drag racing profile kind of emulated from what someone would see in a typical season of drag racing. About 4 weekends, 10 passes each weekend, totaling 40 total hits.
Autocross next. It's really difficult because it's so dynamic.
It's not like going down a drag strip full throttle the whole time. Your throttle is really varying throughout those corners. We base it off of Brainerd International Raceway's Donnybrook road course, 2 to 2.5 minutes a lap, 3 laps, and then a cool down, and we cycled that throughout testing.
Total time on the autocross, do you remember what that was?
It was about 8 hours.
Last piece of the puzzle was the daily driving.
We ended up landing on 15 hours for that, and that was a combination of street driving, highway, and then freeway too, because you know it's fun to come down those on-ramps full throttle.
Exactly. I know that I would do that. If I had 1,000 horsepower, it would be as fast as I could go.
Me too, Len.
And of course, staying inside the speed limit. So Garrett, we selected Dominator for this engine. And specifically here, we're talking about the valve train as it relates to the zinc and phosphorus package. Dominator has elevated levels of that. So when you get into the push rod, rocker arm interface area, you're gonna hit a performance level that you need to have that in there or you will see wear. So that was kind of
correct.
Some of our reasoning behind using Dominator instead of the Signature series on this particular project. Garrett, we're standing in front of a table full of engine parts. So after that 25 hours on the dyno, general comments about how this worked?
Len, after 25 hours, this engine looks great. The rotating assembly looks amazing, the bearings look good, and the valve train looks great as well.
Get into this thing a little bit deeper. Let's bring in Chris Orr, who actually built this thing.
Sounds great, Len.
We've got Chris Orr here. Chris, you are the mechanical lab manager.
Yes, sir.
Let's get into it a little bit.
We set out to build 1,000 horsepower engine, LS based, and we wanted it to be not something that would just make 1,000 horsepower once or twice, but something that would do it consistently for whatever our testing needs might be. You know, we're in the business obviously of testing oil. We didn't want to test engine parts. So that was the challenge, was to build something that'd be durable, something that would run on 91 octane, and we could use it for years to come. You got to start with a good foundation. Things have to be round, straight. Machining tolerances are key as you make more and more power. If you don't have the right tolerance, you don't have the right clearance, you can put whatever oil you want in it at that point, it's not going to work.
So we spent a ton of time just making sure all of these high-end parts, mind you, were the size that they were supposed to be.
For example, crankshaft and rods, the rotator, we selected AMSOIL Performance. We've got their fully counterweighted. This is actually a billet version of their crankshaft. Factory dimensions, OEM rod journals, OEM main journals, good materials and machined correctly. Journals are on dimension, so you can set your bearing clearance correctly. There's no taper across them. When you lay the crank in the block, it doesn't wobble, it's true. Same thing with the rods. Tom Molnar, his rods tend to be very much on dimension. You look at your side clearances on your rod journals, which helps develop that oil wedge. You look at your bearing tolerances, 12 and 6, they're round and they're straight, and that really helps.
And when we're doing an oil, you know, we're doing a test where we're actually looking at the performance of the oil, all of that critical to getting a good looking bearing.
Absolutely it is, and that's things that, you know, we as assembling it really can't change. That has to be machined correctly from the beginning. So we put a lot of time and effort into this thing before it even became an engine, if you remember. Actually bolting the engine together is a very quick process. It's all in the design of parts and measuring everything to make sure it's correct before you put it together.
So once we got that foundation really built and everything was where you wanted it as far as tolerances, measurements, the conversation moved towards, all right, how are we gonna get to that 1,000 horsepower? And you mentioned earlier, you know, we agreed on pump gas. So then we went, well, how about a Whipple? To which you've got some knowledge with.
I do, yeah. I run Whipples in my personal race program. I think dating back, I think first one I had was in 2011. I've run their 5-liter stuff. I've run their old 9.8 liter. This is a 3-liter modern generation. For 1,000 horsepower, it's well capable of that without being oversized. What's nice about them, they're a very efficient piece. They move very consistent air. Whipple sells them with the full intercooler. When you're talking pump gas, keeping your intake air temperature down is very important.
We've kind of cleared that pump gas hurdle. The Supercharger is going to help us with that. Control system. It's a fuel injected motor.
Right.
We selected Holley. Tell me a little bit about how that worked.
The Holley system, it worked very, very well right out of the gate. They provide can tune. It wires in very easy with the detonation concerns and with all the other things we've talked about. Precisely controlling when that mixture ignites is also critically important. The Holley system provides us the method to tune both the fueling and the ignition.
Let's talk about this thing on the dyno. So the engine's together, we were happy with it. It's tuned to a certain degree. We did 3 things with this engine, right? It was horsepower, it was autocross, and then it was a decent amount of daily driving was done with this thing. So we started with horsepower pulls, which one could argue was fairly stressful. What was your thoughts on how this thing ran on the dyno?
It ran very, very consistently. Once we got to that 1,000 horsepower safely, we were able to kind of characterize what that looks like. And then we were just repeating at that point.
I remember seeing the dyno pulls, and we both commented on that. It looked like one line that just kept getting fatter. So it was fairly consistent as it repeated on those horsepower pulls. And then we threw you a curveball. Then we said, okay, we want to take this thing racing on a track, but we don't want to put it in a car. Right? We don't have a motoring dyno. Right? So the decel was interesting.
Yes.
But so you mainly focused on the accel rates, or what went into that?
I looked at a local track actually. We set up an autocross profile to run through that 2.5 mile road course, following all the turns. We ballparked a mile an hour that a driving car, not necessarily a race car, but a car that this engine might find its home in. Might make it around that course in. We ended up averaging I think 200 horsepower over the 2.5 minute lap with a peak up over 800 horsepower.
Right, so you were making 800 horse coming out of some of those turns. In a normal car that doesn't have good tires on it.
Yeah, it's not going to go very far.
It's going to spin.
Yes, absolutely.
So we were definitely putting some stress on there.
Yeah, when we ran that road course first, our oil temperature was pegging past 275, heading towards 300 in a matter of minutes. So, I mean, we were definitely running it hard. So.
Right, and that was kind of the key for that actual piece of this program was to put some heat in this engine, because drag racing, some people don't understand, it doesn't put any heat in the oil. So the last piece of the puzzle was the daily driving. What did we do there?
The daily driving ended up looking mostly like a detuned version of the autocross.
Because this engine, at the end of the day, will find a home, as you said, in a vehicle that spends time on the street. So it couldn't just run on a dyno or a racetrack. We had to do that to it. Because the average human is going to drive it to get groceries or pick up the kids, but then also race down the on-ramp.
Right, it's a proof of performance. So like any proof of performance that we try to do here, we want it to be representative of how something would actually be used in the field.
So we filled it out with that. You guys beat it up on the dyno pretty nicely. We took it all apart, and here we stand. How did it come out? I mean, let's talk a little bit here about results, just a conversation. We started on the bearings. Let's start there.
You can take a look at the bearings, and short of a little bit of foreign particle that ran through the number 1 here, and you can see it in the corresponding upper shell.
But then we move on.
But yeah, I mean,
these moving down the row here.
It's hard to tell these from new. I don't think you could get a much better result on the main bearings than what we have there. So
let's talk about what's actually going on at this power level and why we were so laser focused on these bearings. What were we really watching for?
The elephant in the room is the crankshaft is going to flex.
There you go. That's what I was looking for.
So
this thing is not going to stay straight at 1,000 horsepower.
No. The more power you make, the more it's going to flex.
The key is accounting for it.
Yep.
And we did that with bearing clearance.
Yep. Bearing clearance and oil viscosity, oil pressure.
What was the tolerance on this?
3.5 on the mains with a 50 weight oil.
Moving on to the rod bearings. These things are carrying a lot of stress.
Well, the rod bearings are, like you say, they're pretty well the most highly loaded components in the engine. So if you want to look for bearing stress.
There was a lot of discussion that went into these bearings being uncoated. They're going to show that they were working, but in your opinion, these bearings, these are not bad, these are not beat up.
Certainly not for the conditions. At the end of the test here, we have what I'd call just a light polishing. There's no overlay fatigue. There's no significant wear to the upper bearing. There's no indication that these wouldn't live for a long time to come.
You said early on, and it was a statement that I still remember, we're testing oil, not parts.
Right.
It was your idea to dry sump this thing. Let's explain why we decided to do that.
Well, the dry sump, a lot of times you see that in like autocross type of applications or anything with high G-forces side to side, right? Obviously on a dyno installation, we're not gonna have that. The real reason behind why I wanted to move to a dry sump system is we're looking at sustained high RPM. The LS platform uses a crank-driven oil pump, which means it spins at crank-driven speeds. A lot of engines older engines at least, use cam-driven oil pumps. They spin at slower speeds, move higher volumes. The crank-driven oil pump can have a tendency to cavitate, especially with sustained high RPM. If you get cavitation, you're gonna put air into your oil supply, and air is a lousy lubricant. So it will not produce good-looking bearings. And then we're testing pumps, and we're not testing oil.
Right,
So,
and at the end of the day, the oil is going to take the hit for that, and that's really no fault of the oil.
no,
That was a part selection.
and it'll be very, very hard to tell, what caused that lack of oil there when we're looking at the results and we don't like them.
So that was the reasoning behind putting a dry sump on a dyno motor. Let's talk about pistons. Let's talk about how that looked. This is a relatively short-skirted piston, and the LS are known for, when you stroke them a little, they pull the piston out of the block. What do you think?
Well, we did an LSX block, number one, I guess, out of the gate, because that gives us a little bit longer cylinder. That helps. The LS3 that it's based on has a factory stroke of 3.622. 3.622. We opted for a 4-inch stroke, which, with the longer cylinder bore, puts the piston in relatively the same position that a 3.622 would in a regular LS block. All in all, like you say, they do pull out the bottom of the bore a little bit.
Yep, you can see it.
So you get a little bit of rocking. It's a J&E piston. This is a custom piston. We worked with this dish design here, and we've got an upgraded pin in it, DLC coated, nice thick wall stuff, all for durability in the application. We get a little bit of skirt wear, but dimensionally, these aren't collapsed in any way. They still measure just like they did when they were installed. The ring grooves are all in excellent condition. The piston rings are all in excellent condition. So and again, the engine vacuum throughout testing was very, very consistent. So we had good cylinder seal that wasn't compromised. So
and these could go right back in.
These could certainly go right back in. Yeah, the engine was by no means out of breath or tired in any way.
Right.
So
people will ask why we did that custom piston, and we did that mainly because the compression and the pump gas requirement of this engine.
absolutely.
The bores look really good too.
The little bit of wear that we see in it is from the bottom of the bore, not from the top of the bore where your peak cylinder pressure is. Everything looks really happy up there. It's the turnaround on the bottom.
Valve train. This is what I would consider a high-end valve train.
It is. So this is Jessel shaft system, Jessel roller lifters, DLC coated, very, very nice stuff. I mean, after all the runtime that we have on it, if you spray the oil off of these and put them in the box, I think you could.
I don't think you
could mistake them for new.
There's no way you could tell.
No,
I mean,
really.
they are pristine.
It's got a trend push rod, custom length for what we needed. We ran a Manley spring setup, and we ran a fairly high pressure, solid roller. We were in the 750 to 800 pounds over the nose.
Yeah, and that's a chunk.
yeah.
That's not a production motor.
No, definitely not. It's not a hydraulic roller cam engine. It's a solid roller set up for valve train that could, honestly spin quite a bit higher than we probably ever did. But our interface here, you get some decent amount of pressure and loading that's going to go between these two surfaces. On the intake valve to some extent, even more on the exhaust valve, because the exhaust valve has to open against cylinder pressure.
And what we saw here and what we were looking for was no wear here.
Yeah, we really have no wear on the push rod tips. Everything
nothing.
looks very, very, very nice. So.
And shameless oil plug part of this. Yeah. That's where the Dominator oil with that elevated zinc and phos, that zinc really helps to protect that surface, right? Because it's going to activate in those different areas. And that's what really is going to start separating, a production type oil that goes in every kind of type of a car to an actual purpose-built racing oil. Cylinder heads on a supercharged motor. We like this AFR. Why?
Yeah, AFR specifically. Again, it kind of goes to my experience. I've run quite a bit of AFR product myself in applications at higher power levels. They advertise it's big to them, and I believe it. They have a very nice thick deck on them that holds a gasket well. We also, in this build, because we didn't want to test parts again, we went with a 6-bolt, which an LS engine is typically a 4-bolt design. And at 1,000 horsepower, you're going to probably get mixed results. If you have any erratic combustion at all, you might get some bad results. So we were able to upgrade with the 6-bolt design. And the other deal with these is they were actually the Jessel shaft system that we ran is designed for this cylinder head casting. So it was really a nice package to put together something that would be bulletproof. And they do obviously provide plenty of airflow for the horsepower goals that we were looking for. With the given size engine that we had and the RPM that we were looking to run, it worked well.
Well, Chris, I think this was successful. You know, I think we did a pretty good job here of covering our bases. Nothing caught us out of the blue, right?
No, I don't think so. I think the project went well.
That's it for this one. I don't think we're done with this engine, so stay tuned for more to come. Now, regardless of your performance needs, regardless of your oil needs, we've got you covered. So check us out at amsoil.com.